So I just wanted to go through the two. There's like two papers for the final. Let's see. Any questions? Anything from the other thing? I guess we turned in the 14. I didn't look yet, but yeah, it's all right. Just do this. So there's like basically two homeworks. Like one's on colloidal gelation, and the other's on this kind of crystallization in a confined geometry. This is kind of a surface chapter one, and this is
So,
yeah.
so question C, that link is not working.
Yeah, you have to just copy it. I don't know why the link's not working. It's a link that's automatically made, so I didn't,
Oh,
but if you copy that and put it there, then you can go here. This works.
okay.
And then he's got this it's basically just he tells you how you get this equation,
Oh, no.
how you convert the potential to the second Verrow coefficient. I mean, it's pretty short. Yeah, so I don't know why that link, like I didn't make that link, so it just automatically made it. And anyway, so there's two papers involved in this. Um, so anyway, they're both, well, the questions on, well, anyway, I'll just go through them, right? So let me get some notes on these. Bunch of notes. Notes. So, um, um, so anyway, the problem here, this is a Proceeds National Academy of Science, just like a high level journal like Nature, Science, and this is one of them. The difference, this one, if there's a thing called the National Academy of Sciences, which supposedly the top scientists in the US are in it. And then they have this as their journal for that group. So if you're in that group, you automatically get a paper published. But if you aren't in that group and then you submit it, it used to be you had to have one of them suggest that the paper get published in it. But now I think they take papers, ordinary papers. So anyway, it's supposed to be high level journal, I guess. I'm not sure how the citation index goes on it, but anyway, so they're looking at gelation. So this is and the kind of gel that they're looking at is basically mayonnaise. Like you have oil and you have water, and then you have some kind of protein, which would be like egg, I guess, and mix that together and you get mayonnaise, basically. So this is like colloid, so that's a gel. It's kind of gel. So those linker molecules connect together the oil droplets. And that here it's nano size. So he's not using mayonnaise, he's using PDMS, so silicone polymer. And then this is water, and the linker is this PEO. Oh, I didn't bring I got these markers up. That's good. So PEO is this flat polymer. This is water soluble. It's also called PEG. So PEO PEG, and then at the end of it has this acrylic. Well, there's a double bond in it. You notice pH here, 1, 2, 3, 4. I guess that's that's the acrylic. So you can, this is acrylic. So that thing you can polymerize that part if you want. Or the way he's using that, this thing's oleophilic. And this is hydrophilic. So that those things can kind of link up the oil droplets like egg would do in a mayonnaise. Right, so you can make your own mayonnaise. It's pretty easy to do. You have to stir it a lot to get the droplets to break apart. Anyway, so how does that gelation happen? So he says he says in here there's like multiple mechanisms. And all right, so the problem he's addressing is there's multiple mechanisms for gelation, not just one. There's 3, in fact, that he brings up. And then there's a lack of unambiguous determination of gelation as it relates to a phase diagram. So he's talking about phase separation. So in the end, he wants to have a map of. So the final thing's a little figure here somewhere. These are appendices. Is this the final thing? Equilibrium, non-equilibrium. I think that's the final thing here. So I'll make this larger. So he's got second viral coefficient. So that we had take the van der Waals model. That's going to be this is the excluded volume. And then it's this is the binary interaction energy, whatever. So anyway, he's saying B2 is like 1 over T because of that. This is a van der Waals equation, van der Waals interpretation of second variable. Right, so he's saying that he can, and the reason why he's not just using T is that he's comparing, so this axis is kind of 1 over T. So, all right, and then then he's going to determine, he's going to do computer simulations to get this gelling. He's also going to do neutron scattering measurements to get this B2. So the reason he's using B2 instead of temperature, so he can convert the neutron scattering into B2. And then he can also convert the computer simulations into B2. And he converts the computer simulations into B2 using that equation that you were just asking about, this equation. So computer simulation, he can get the potential between the particles. And then he has the temperature he did the simulation. He has the hardcore size of the particles, so sigma is the same thing as, so B is basically sigma. You have colloidal particles. So in a simulation, he has these colloidal particles of size sigma. And he's going to have potentials that go out to like 2.63 sigma. So his potentials will end at that point. So the particles can be closer than that, or else you won't consider that. And then so this is excluded volume. So this would be B would be sigma cubed. Right? So if you forget about A, then you have just sigma cubed. So he normalizes B by sigma cubed because that's the units of B. So it kind of makes sense to do that. So this sigma cubed kind of comes from a van der Waals picture of B2, more or less, somehow. So anyway, anyway, that's part of this. So he also, you can get from scattering, you can get B2 directly, like I showed you at some point that you do I by concentration. So I scattering intensity is proportional to concentration. So if you reduce that and plot it against Q, and you find out that you have some structure, and it'll at Q goes to 0, you get some number here, and as you increase the concentration, this is reduced by concentration. This thing actually drops. So the intensity gets higher with concentration, but you've reduced it by that. And you see this drop, and kind of the rate of that drop is B2. If you do a concentration series, you can get B2 from scattering directly. He doesn't do that though. He does something a lot more. That would be the normal way to get B2 from scattering, neutron scattering. So he gets it by, I don't know exactly what he does. It's in the appendix, but basically he gets these potentials. He gets a potential from it, and then from the potential curve, he calculates B2 using the same equation that he uses with the simulation. The simulation, you directly get the potential. I mean, that comes out of the simulation because you're getting the interaction between the particles, or they're going to interact with each other. There's some potential here. So you directly like measure that as the simulation goes on. It's a LAMPS simulation. So it's molecular dynamics, but the molecule is just spheres. It's like you swap out spheres for molecules and you use a 612 potential or something for the interaction. He's not using 612 potential. He's using some other exponential potentials in here somewhere. Maybe, yeah, I think he doesn't use 612 for this. Both papers have simulations. So it's a little confusing, but so this is the LAMPS thing from Sandia. That's like a shareware thing you can download. And then basically he puts a potential in and he does a simulation based on that. And the simulation parameters he gets are from argon. Like in other words, the potential of interaction is for argon atoms. And then this other thing is oil droplets with this the other thing. So it's a little bit of a mismatch between what he's simulating and what he's doing an experiment on. And in the experiments he did in another paper, like the data just comes from some other paper. So anyway, that's part of this. So the question is, like, he's got three models for three mechanisms that can talk about how gelation happens. The first one is a percolation model. The second is a phase separation model, and the third is glassy arrest. So he's got these three things. So this is a kinetic model. This is a structural model. And this is a thermodynamic model. So hence he's going to have, like in that final plot, he's going to have like three curves. He's got the three, wherever that. So he's got regimes within this. And I think the triangles are let's see, he says down here. So this is a critical point. The hollow triangle is a critical point, and this is a phase one, so number 2. So he's saying like all right, so this is really an LCST because this B is 1 over T. So if you drop B, you're raising T. Right, so he's getting to a 2-phase region by increasing temperature. So it's an L phase separates on heating, which PEO does that. This thing phase separates at 60 degrees. So he's basically getting a lower critical solution temperature. The lower critical solution temperature is right there, and it's going to be 1 over that B value times some constant. And then so that's the phase separation curve. And then I think the squares are his actual gelation measurement. So he gets those squares by doing this oscillatory SAOS, small angle oscillatory shear rheometry. So he's got a disc on top and a plate on the bottom, and he's going to oscillate this thing at like 1 degree oscillation, and he's going to go across different frequencies. And what happens is, if you look at that, you're putting a strain on it, a stress on it, like a sinusoidal stress oscillating, and then the strain that results like is offset from that. So you get this shift factor. If this is 2 pi, and you have a phase angle that shifts the stress from the strain. And this is like a shear strain going on. Maybe your gel stuff is in here. So so that means you can get the modulus, the shear modulus is going to be the shear stress, which is usually like that, and the shear strain, which is usually that. Right, but this modulus kind of changes depends on the frequency that it's being stretched. So it's going to have this phase shift with the frequency. So you have like cosine of this del times the real part plus an imaginary part. So this becomes a complex modulus because if this thing was totally liquid, then this del would be like 90 degrees. And if this thing's totally solid, then that del would be 0 because they'd be right on top of each other for hooking elastic. So depending on how they separate, the more they separate, so liquid, it would be over the set of P. So I've drawn it almost at a liquid. If it was a solid, they'd be on top of each other. Like a solid is hooked in, it's just a spring, you pull it, it moves. Like this in a liquid, you pull it, there's a lag because it's going to be that the stress is going to go with the viscosity times the strain rate, like the derivative of the strain. So it's going to be the derivative of the sine's cosine, so it shifts it over by 45 degrees. And so that's kind of how that works. So they're like liquid and solid, right? So this del kind of tells you what the shift of that is. Anyway, so you can plot G prime and G double prime. G double prime over G prime is a tangent of that delta because sine over cosine gives tangent. You get cosine sine. So tan delta is G double prime or G prime. If G prime is bigger than G double prime, it's a solid. And if G double prime is bigger than G prime, it's a liquid, quote unquote liquid. So if you can tell when it gels, because that's when this G prime over G double prime would be bigger than 1, then it's a solid. Okay, so you can define something like the ratio. So you can do this measurement. You can get G prime to double prime. You can plot those two to find where they cross, and that's where you have a gel. So he does that. I mean, that's actually the technique he likes to do. So the solid ones are the solid, and the hollow ones are the G double prime, and where they cross is where the star is. So see, instead of doing this as a function of temperature to watch a gel point, he fixes the temperature, so he fixes the B. So B is 1 over temperature, so he fixes the B, and he varies the time by varying the frequency. 1 over the frequency would be the time. So he's got the time, and he's got this cross point, and that's his gel point. So he's got a tau, and he's got a B because it's a temperature. So then you can just say, I can plot B versus temperature. B versus time somewhere. B versus time, there's a plot of that somewhere. Cross over time, and then B. And then he says that, so if you want to know, so at long times, so at short times it gels faster. Long times it gels like it'll gel at a more equilibrium point. So the longest the time, that's equilibrium gelation, which there's no other way to kind of get it. So you can't measure at infinite time. So he plots versus 1 over time, and he gets a linear dependence, and he finds his B star as the intercept to that. It's a little complicated. It's a way to get B star. The simulation, in simulations, you don't change the time. In simulations, you just get B stars out of this. So this is from the experiment to get B star. So he's measured neutron scattering different times to get the Bs. And he's got this gel time from a separate experiment from this rheology measurement. And he finds his B star number that he wants. It's a lot of measurements. And he's going to go back and plot that for different concentrations and map out like how this stuff behaves. All right, so each of these, so at a fixed concentration, each of these is at a different frequency. So fixed concentration, change the frequency, get the B, which is effectively the temperature. And then you can get this kind of plot. So anyway, he's trying to map out, like, he has these three mechanisms. He wants to know like where they come into play. So obviously, like, or maybe obviously at high concentration, you get the glassy because things get stuck at high concentration. So the glassy would be like the high end 3 and 7. And then in between, you have this flat, this is the gelation curve. It occurs at the same temperature for all different concentrations. It doesn't matter. And then he gets to like gels that fall apart. So they're shells that first form and then destroy themselves because the gravity rips them apart because they're at such low concentration, they gel, but they fall apart. So that's this regime 1 and 4. And 1 would be in the single phase, 4 is in the 2 phase. So if you're in this region, if you're in the region in the middle, so it looks like there's a fixed distance between the thermodynamic part and the gelation part, right? Like the two things are related to each other. Once you get out of that region, then it falls apart. When you get into the glassy state, then it's actually just a kinetic phenomenon that the gelation happens, right? So anyway, so there's a lot to this paper. Let's see. So let's see. So I mean, the main plan of his is that, oh, he'll be able to tailor gels. Like he'll be able to tailor this gelation phenomenon, which is used for a lot of different things. Sometimes it's a problem, like in oil recovery, when you drill down at the bottom of the ocean, if the goo in the pipe gels up, then the whole operation ends. And you got like a 3-mile tube going down to the bottom of the ocean, and it's clogged with a gel. So that's a nightmare scenario. It happens. And then if you want to do drug delivery, then you want to have a gel, you want to control when it releases. So that's a positive feature of gelation. So it's positive and negative that would draw interest, I guess. And it's gelation's kind of an interesting thing too in general, I guess. But so let's see what else. All right, so that's kind of what I have here, I guess, on this. It's a 12-page paper, so it's kind of long. There's a lot to get out of it if you want. He talks about the lamps. He talks about the details of the simulation. We're not that interested in that. If you're interested in it, you can kind of look that stuff up. The lamps is all available in just Googling. If you Google whatever word and then lamps, you can find the whole thing on it. So if there's something that's confusing, it's pretty simple to work with it. So what else do I have here? Let's see. And the gel line. That's pretty much what he's doing. So he color codes the whole thing to these like red, blue, green. So it goes A, B, C, D, and goes around in a counterclockwise here. It's like an odd way to put labeling, but so in the blue, again, like the thing is such a weak gel. So it gels, yes, but it falls apart. So he's talking about this gel collapse, and D is the green one is this happy one. So it's like green go, intermediate gel quench depth dependence. So it depends on, in other words, again, it's like there's a fixed distance. So this is phase separation. What he's thinking is phase separation driven, the thermodynamically driven gelation, number 2. Um, so I guess A is almost like 1, I guess percolation. I mean the B here and the green one's kind of the phase separation. And the red one is this glassy arrest part. So you see that for the glassy arrest part, let's see, there's another plot here. Not that plot. There you go. So this, all right, so the these are the primes. anyway, there's more to it than that, but let me just find this one plot I'm looking for. Not that one. Oh, it's in the appendix, I think. Uh, no, I guess it's this plot. So here, when you're in this region, it's at a fixed, no, let's see. For the glacier rest one, something's constant. I don't remember what. Let's see. There's a bunch of things in the appendix here. No. Not really getting exactly what I want. The bottom end is comparing it to some experimental systems, like these other systems in his mayonnaise system, but uh yeah, I don't see what I'm looking for here. It's not that plot. Uh I guess it's at this has a fixed, so the green has a fixed modulus. So G prime, G double prime are the same across for the different temperatures. Or for the green one, and for this one, they're different. And he explains that in the text. I don't remember exactly how that works. Anyway, it's kind of a long paper, so maybe just skim through it and try to get what you can get from it, and then see if you can do these questions. So what we got here? Some of the questions don't have to do with the paper, but so there's these three kinds of gelations. He describes that in detail at the beginning, like in the introduction. Uh, three kinds of gelation. And I think he just used logic a little bit, but percolation, and this part is thermodynamic, and this part is glassy transition. So you can kind of read that and answer whatever that is asking, Get three kinds. How would the thermal dependence of gelation differ for the three mechanisms? So he shows in the paper like the thermal dependence is, I think it's fixed for the phase separation, and for percolation, it's like it's kind of, the first one is kind of doesn't have a thermal dependence. This one's totally dependent on the phase diagram, and the glacier rest is a kinetic phenomenon. So in the sense that like the kinetics depend on the exponential of energy over kT, like the viscosity, then that one's got an exponential temperature dependence. And the phase separation one is kind of constant because in that region the phase diagram's flat. So in the region where the phase separation governs it, the phase diagram's flat in that region, and that's basically, there's no temperature dependence. So it depends on the temperature of phase separation, but that's constant in the region where it applies, so it's constant. And then the glassy, both the collapse and the glassy have a strong temperature dependence. The glassy, because of this dynamics, like the collapse one, I'm not sure why the collapse one has a strong temperature dependence, but it's just, there's only 2 points in that region anyway. So each of these three mechanisms, gelation or thermodynamic transition. So then I think you have to say what a thermodynamic transition is. Like you can say there's some difference in of quantity that you can talk about. So here the quantity is like a kinetic quantity, like the viscosity. So that's not a thermodynamic transition then exactly. If the viscosity defines it, then it's not thermodynamic. If it's something that's governed by the phase separation, then it's thermodynamic. And the other one, the percolation is just like a structural thing. So I guess you could say that the two states have a different kind of branch content, something like that. So, and that way might be distinguishable. But if it's not really governed by temperature, so see, there's not a lot to be said about, is it a thermodynamic transition or not? And then, so if it's a thermodynamic transition, kinetics shouldn't play a role. And if it's a glassy arrest, then kinetics plays a huge role. So it depends on how you look at what the gelation is. See, these rely on you kind of defining what gelation is, which in context of those three models, I guess. It has a different answer for each of the models. Then what's the difference between a state diagram? So he's talking about a state diagram and a phase diagram. So state diagram, he's using the word state diagram because it isn't a phase diagram. That's the basic idea, that you can draw a diagram that's something versus temperature and call it, some people would call it a phase diagram, some would call it whatever. So there's a little bit of a, he's trying to get a thermodynamic basis for the thing. So, and then this guy Cates is popping up all over. So in the soft matter thing. So anyway, he's quoted in here, and in fact, he's kind of basing it on this paper by Cates. Like a lot of this paper is based on a paper by Cates. Cates is a guy at Cambridge in England, so I don't know, he did his PhD with a Nobel laureate, and he's kind of in line for Nobel laureate. So if whenever the turn for England comes up, like it goes country to country, so anyway, so Cates and coworkers pose that, this is from quoting from the paper, that quenches at different rates could be used as a means of controlling gelation behavior when the timescales of phase separation intersect with the timescales of the quench. So so there is a rate of phase separation, and then there's a rate of temperature drop where you're driving the system to get to the gel. Like you cool down Jello and it makes gels when you cool it down because there's some interaction between the proteins and water, right? So it's a suspension of a network of proteins that make Jello. Anyway, so there's a time, there's a rate of the phase separation of the protein in that case, and there's also a rate of gelation that's going on, and those two things have to have the right relationship in order to get a gel. Otherwise, you get globs of Jello, you get bobo balls or something, right? Instead of Jello, a solid Jello. So anyway, there's something to be said about that. Like, you just think about it, and maybe I think you can just say something about it. And then the minimal gel point. So if it's a kinetic phenomenon and you can't reach infinite time to get the gelation, then you need to do this extrapolation. So the minimal gel point is basically that he runs into this problem that defined an actual one point that's a gel point. It's a moving target. So the way that he gets that is by doing that extrapolation, whatever that was. This thing, so he's extrapolating back. And when he does that, it sometimes it doesn't work because some other, in other words, it's two linear, he says this has two linear regions. It doesn't look like it exactly, but basically that part and that part. He says this is the part that matters because it's closest to the infinite time. This part is where there's some interference with something else going on in the system. He talks about it in the paper. So basically that extrapolation is this idea of minimal gel point. Like you have, this is temperatures, those are gel temperatures, and that's a minimal gel temperature, 1 over the minimal gel temperature. And equation 1 relates, so equation 1 is that thing, and then that's how you calculate, if you know the potentials, how do you calculate the second Viral coefficient? So he says this link tells you how to do that. And then so that for if they're non-interacting hard spheres, so you have, this is the interaction, binary interactions, so non-interacting is at 0, and you just have B2 is B, and B is sigma cubed. So when he divides by sigma cubed here, that's the hard sphere non-interacting. So that's the van der Waals. sigma cubed, and the rest of it is from this other, wherever that thing went, if it's still open, this thing. All right, so this ends up with the same equation somewhere here. It's basically the integral of the potential, exponential of the potential, the KT, like a Boltzmann factor. So let's say, actually, it's almost like this is an integral, this is almost like a partition function, right? It's the integral of the Boltzmanns. So it's something like the partition. Anyway, so it's that business, and this is this thing about the G prime, G double prime. Is that me or something's buzzing? Not me. Yes, it could be me. Right. So, all right. So, temperature oscillation is new. How would Fenton's figure 3a be used to predict phase behavior? Fenton's 3a, 2, 3a. So, I mean, in this, all right, so this is like the line is, if you're talking about a state diagram instead of a phase diagram, they have a liquid and a gel state. So that is kind of a phase diagram. And in under the second option, phase separation, the thermodynamic model, there's a relationship between this gel point and the phase separation point that you can see in the last plot, in this plot. Second to last. So there's a fixed distance. So you phase separate, and at some point in the quench, this is a raising temperature quench because it phase separates when you heat it. So then you find a point where you get gelation. So the two things are linked. So if you knew what that delta T was, you could predict the phase diagram from the gel point. Yes. I guess that's kind of what you could do. Explain the three regimes, red, green, blue, and Fenton's 3A. So they're kind of related to those three things, but not necessarily, right? So this part is where it's too weak to withstand its own weight and it collapses. This is a phase separation driven gelation. And this is a glassy gelation with a high concentration. So it's kind of what that is. E, because a time scale dependence to gelation. All right, so this is not in the paper. So this is an idea that if you do a simulation, so say you have a box to do a simulation, and then you're going to have like X's and O's in it. Right, and then you would define gel by when I can make a pathway through it, that would be gel. Right. So that's at a small scale. And at that, so say I could flip X's to O's, then it's not a gel. And then somehow I'm doing a simulation where I'm going to go, I can calculate the energy for the system, like E0, then I switch to X to O, that's E1. If E1's lower than E0, then that's good. If E1's bigger than E0, then I take KT delta E over KT exponential, like a Boltzmann factor, I get a probability of delta E. Then I compare that with a random number. I compare those two. If the probability is higher than that probability, you'll accept it. That's called a Metropolis Monte Carlo simulation to do that, right? So I can run that, I can let that run at some temperature. So this is by T. So the temperature is going to govern the separation. If I change the temperature, I'll get a different structure from it. Lower, like in a normal system, lower the temperature, the more it would pop to axis. Yeah.
If you switch it.
Yeah, if E1's less than, sorry, if E1's less than E0, I take it. So I've lowered the free energy. If I lower the free energy, I'm happy, that's good. And the energy is calculated because these two have some energy, small energy, and these two have some small energy. And then two X's have some small energy, so we can sum up the energies. I just randomly flip one and I get a new energy. I sum all the energies, so that's the sum of all these energies of all the different states you have for every bond. So each one has four bonds, I guess, and then six if it's 3D. So, and then you just sum up all those for the box, and then you just can let that run. And you can do, that's called the icing model metropolis Monte Carlo simulation. That's like one of the frameworks of simulation, right? So anyway, so you can run that and get spinodal, you can get total phase separation, whatever you want doing that, right? But the problem is, like, this is small scale. It's easy to get percolation, because it's like just only has to have 6 of them in a row and it gets it. But if I make it 1,000,000 big, it's going to be a lot harder to get percolation. So there's a size scale dependence to when percolation happens, if you define it that way, by this percolation model. And so anyway, so that means there's a size scale dependence, and there's the issue of he doesn't talk about, because he's doing simulations, Monte Carlo simulations, he never talks about the size scale dependence of it. So this Monte Carlo simulation, it's going to be like 100 angstrom size. And his rheology thing is going to be 4 centimeters. So it's something like 1,000,000 times bigger. So he's comparing the simulation with, and the neutron scattering is also like centimeters. So basically he's comparing centimeters to something very, very small. And there's a size scale dependence to what he's looking at. And he totally doesn't talk about that. Right. So anyway, maybe it doesn't matter, but basically that's what this question is. Explain the size scale dependence would be like something like that. Like you'd have to go back to that. That's kind of like the basis for size scale dependence, I think. It would happen too with molecular dynamics. So he's doing lamps. So in lamps, you would see the same thing. Like here in lamps, instead of doing this Monte Carlo, so in the molecular dynamics, he's going to have like these things flying around some velocity, and they have some mass, and then they're going to have potential energy, and they're going to kind of bounce off each other. You have some potential energy function, like the 612 potential, something like that. It has attractive, repulsive. So each of these particles, so it's going to have like, you're going to do some random motion and then recalculate the total system energy again, and then let the system run on its own. Basically, it's Newton's laws are going to move the particles around. The repulsions, they have velocity and momentum. You just let them kind of move. All the particles at once are moving. So you go through time steps. There's like steps of motion, and then you recalculate the energy, recalculate the density, recalculate the temperature, which is like 1/2 mv squared. The sum of all those gives you the temperature. So you get the temperature, the density, the energy for this like a lamps. So it just runs, like it's kind of mimicking what nature does. This has nothing to do with nature. This is just like you're flipping things. This has a lot more to do with like a gambling game where you flip the card. This is actually like trying to make a model that looks like what nature looks like. They both can give you the same answer. You can model all the systems with each of these, but there's nuances to the different ones, right? So, right, that's what he's doing in this paper, the lamps thing. But also, that would also have a size scale dependence, because in the end, it's this test of like the pathway. So if it's a smaller grouping, then it's more likely you get phase separation, because you only have to have like heads 4 times to get percolation. If it's 1,000,000, the odds of that are going to start to get lower, right? Well, you have more paths, but basically it's harder to get percolation on a large scale if you're simulating, right? And the macroscopic is this huge scale, right? So you'd need to demonstrate scale independence before you could really say if the thing works. That's kind of the idea, but he doesn't do that in here. So that's that. Anyway, the idea is like we can kind of work on these. You got a little bit of time and look at them. I think it's kind of doable. That's the first one anyway. The second one, The second one, I realized like the questions aren't necessarily about the paper that much, even though, so you don't, let's see. So this goes blah, 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 da, 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 that's the problem. Then it says like the normal derivation of Gibbs-Thompson. This is the Gibbs-Thompson equation. To derive it, so that's what I did in class. Any questions on this one? I'm gonna erase it. But once, twice, three. All right. So we had that equation. If you're talking about an infinitely large crystal, then you're at, call it T infinity. And then delta G equals 0 at the melting point. So T infinity would be the melting point. And you have delta S equals delta H over T infinity. That's kind of the definition of delta S at equilibrium. That's like added phase transitions like crystallization. Right, and for a crystal, the size is infinity, like it's a full crystal. So if you have a smaller crystal, and this is all volumetric, if you have a smaller crystal of size R, then you have delta G is going to be the volume, which is going to be the surface area times R, and then times that same thing, which is delta H times 1 minus T infinity over T. Because delta H over T is delta S. So when you're at R, it's a different T, it's TR. And then there's the surface terms. You have like plus the area, and then the gamma surface tension. But the surface energy is so and if you say that's going to be at a metastable equilibrium, and say that equals 0, the areas cancel, and just have R is sigma over delta H, and this weird 1 minus 1 over T infinity over TR. So you can call this TR over TR, and then pull the TR up here. You just have TR minus T infinity here. That's a Gibbs-Thompson equation. Right, so you have this is a quenched up, and this is the temperature of crystallization. This should be T infinity up here, but no, it's T infinity. Anyway, so anyway, that's a Gibbs-Thompson. So he gives that. So that's what it's asking to derive it. That's what I'm asking you to do here. Do that. Let's see. So he's looking at this problem when you put, so there was a Nature paper, reference 5. So this thing, so it's in Nature Materials. So that's like a high impact journal. And he says, oh, that's kind of interesting. We have a AFM tip, so atomic force microscope, and you're rastering across a liquid. It's a picture of it here somewhere. And it crystallizes at the interface because you have a confined liquid. So this temperature TR is smaller than, this is backwards, should be T infinity minus TR. That one's wrong too. So TR is smaller, so small crystals melt easier than large crystals. The smaller they get, the easier they are to melt. So TR, the temperature drops with R. So basically, if you have a small crystal, it'll melt easier. So somehow he can, in this confined space, he can bring about crystallization. Oh, it depends on whether it melts easier or harder depends on the interaction between the surface and the liquid. So here there's no interaction in this case, but in this case there's some kind of interaction. So if the surface enhances crystallization, So this delta liquid, water, solid, or liquid W, what's W? W is the thing that's being crystallized. So between the liquid and the thing that's being crystallized and the surface tension between the solid and the thing being crystallized, that's plus or minus, you can get a right increase or decrease at Tm. So in this case, it gets an increase in Tm, so it crystallizes in the gap. Right. So this is the way this is done. There's nothing here. It's in a vacuum, right? So it's just one surface energy. But if you have two things here, then it's like it can be the difference between the, anyway, it's a different geometry. He's got a solid, he's got a liquid out here, and then he's got his things in here. So he's got this condition and that condition. So he needs the gamma here and the gamma there. The difference between those two to get this situation. That's why it's the same equation. The equation's like, this is T over delta T, and then sigma over delta H. The two is because there's two interfaces, top, bottom to it. And then otherwise it's the same thing. And H would be R. So this is the same equation as that, except it's got this delta gamma. So the question is just like, see, it has two surface energies because it's not a particle in void, it's a particle immersed in this liquid, right? So those two gammas, you have to have the difference, the driving force is going to be the difference. Then how do you accommodate this in your derivation? So to accommodate that in this, you just replace this gamma with gamma minus gamma. Because the geometry is different. I mean, you need a cartoon to show it, the difference between that and that. Basically, it's just you just substitute for the gamma minus gamma. The two is because there's two surfaces. There's like surface one, surface two. So you have to have a two here. Whatever that is. Where the gamma is, you have a two here. Here it is. Top bottom to it. Then he gives the following thermodynamic potential. Right, so then in this paper, and get rid of these guys. Get that. So he gives these potentials, right? He just kind of writes this and he says the ensemble of thermodynamic potential is a grand potential. He just gives this. So the question is like, what is that thing, this part? So it's got internal energy, TS. So if you do the and if you have like Helmholtz free energy is like U minus ST, so it's a Helmholtz free energy. And that's a constant volume. That's the constant volume one, right? So that's all like U minus TS is Helmholtz free energy. And then he writes U as TS. So U, the same thing. Let's see. So this PAWH is the that's like the PV. That's the PV part of this. So yes, TS minus PV. Anyway, somehow you can, I think you substitute this PV term for, or this is just another way to write the free energy in the construct of a system. I guess that's what this is. H is the height, the gap. So he uses H, and he doesn't talk about enthalpy in here at all. So the only H in this is, he only talks about entropy and internal energy and free energy. So he never talks about enthalpy. So H is always the gap. H is his gap height. Makes it kind of a little confusing, but anyway, so it's just so just explains the origins. So those is kind of what I said there, more or less. And then the free energy, it's a Helmholtz free energy. And then this thing's a little bit more involved. So you have blah, blah, blah. So obtain the, derive the Gibbs-Thompson equations, this same equation, not by that route, but by this route of use this Oswald Freundlich equation, and then integrate the Clausius-Clapeyron equation. So you go, so the Clausius-Clapeyron, see, two. This is just like, see, this doesn't exactly have anything to do with the paper. That's what I was saying. So you have Clausius-Clapeyron. There's a dp dt is p, and L is delta H. And then p squared r. Right, so you can go dp over p, you can integrate that. That's ln of p over p, whatever, p initial over p zero. And then what's left over here is dt over t squared delta h over r, and dt over t squared is d1 over t. That's what we did for the Clausius-Clapeyron thing, and then this ends up giving you 1 over t minus 1 over t. And then ln of p over p0, and then delta h over r. And then the other Oswald Freundlich equation is ln of p over p. So it's like this thing with 2 gamma equals 2 gamma, and then you can make it molar or whatever. So r, and then p, and then the size r. So if you move the r up here, move that down there, you get like this same thing, this thing. So that's what he did for his that's what this guy did for his PhD dissertation. It's like kind of easy to do, I guess, but I mean, there must have been more to it than that, I guess. You know, basically that's what it said in some book. That so for this reason, Kevlin equations obtaining. So do that, do what I just did, and then Oswald. Then give the Oswald Freundlich. So there's this thing also for with the concentration. It's like ln of concentration instead. Describes the relationship between, that's in the notes, like you can get that from the notes. It's the same as this, the log, say log equals that function, but it's concentration instead of pressure. That's in the notes, you know, you can get that, but just kind of use. So this is just give an algorithm from Metropolis simulation of this type. So that's whatever I said before, but basically that's also this thing. So if you look, this is like a wiki page or some University of British Columbia. So it's like so this is the algorithm here. Generate random initial whatever. So it's made from magnets. The box was really magnets and the magnetic spin. So it's, when it says magnetic spin, it means X or O. You know, and then so you have a configuration, meaning that it's a grid with X's and O's in it that has an energy, sum up the energies of all the bonds between the X's and O's, then flip one of them, calculate the new energy, calculate the difference in energy, and then get a Boltzmann probability for that. So beta is 1 over KT. So energy over KT is a Boltzmann, like this would be, you'd sum that to get the partition function. That gives you the probability for the one state of the system. If it's less than 0, the delta E, if it's less than, if the energy is less than 0, you accept it. If it's bigger than 0, then you get a random probability, compare it. If you win the gamble, then you keep it, otherwise you throw it away. So that allows you to have a randomization of the system based on temperature. Then update the average energy and then do it again, like repeat through as many times as you need to until you repeat that until the temperature gets to a constant, right? Or until the density reaches a constant. So you're going to find out when you start the system, you had some density. It's gonna have like a high density, maybe a low density. Then as you run this thing, it's gonna find out the density is changing, and then finally it's gonna find a place where it's oscillating about a value. So like right there, done. Or this could be temperature, or this it could be energy. And at some point you reach where the system stabilizes. So you have to kind of demonstrate that that happened. That doesn't mean, so again, like you can have energy wells, right? You can have something like the global equilibrium's here, and you've reached a point like here in time. So a number of changes you did. So it doesn't, because you reach a steady state doesn't mean it's the final steady state. So there's always a guesswork involved in this. Like, did you actually reach what you wanted? So anyway, so is that business. So this is an important question. Like, you can never know when you reach equilibrium. That's the point of this. Like, you can think that you know you've reached equilibrium because nothing's changing anymore. Then all of a sudden you find out there's a sinkhole under your house and there's the real equilibrium. Yeah. Someone fell in a sinkhole recently. I was reading somewhere, but anyway, turns out sinkholes happen. So even in this simulation, but so, and then E, Scully shows a crystal structure exists at the interface. So this is just go back to the notes and do the thing. This was in another homework, like this, the heterogeneous, homogeneous nucleation. So what's it? So why would you, so he shows in here. So when you're looking at this, you think, wow, yeah, you could use the Gibbs-Thompson that has to do with particle size, and then you could say, yeah, in that confined region, you could get crystallization because of this, the gap size. But you could equally say that it's just that this crystallization. So in this case, this is amorphous, that's crystalline, and you can see that it's crystallized at the surface, right? So depending on how deep the surface crystallization goes, you could get that, right? It might not have anything to do with Gibbs-Thompson. It might just be a surface induced crystallization. So this is just saying to play around with that idea. That if you have, this will have half the energy barrier if you have a surface that nucleates the crystallization. So in heterogeneous, it's half the energy barrier. So that means it's going to be much easier to crystallize. So that means that could explain like why he gets crystals forming. And it might have nothing to do with Gibbs-Thompson. So anyways, that's like I said, none this thing, even though it's about this paper as a framework, it doesn't have much to do with the paper. It's more like just different things. You can look at the paper, but anyway, in the end, he gets something he's happy with. The red is, he wants to show that Gibbs-Thompson works, and he does these Monte Carlo simulations to prove it. This is the whole paper, this last little figure, right? So this Monte Carlo simulation is in blue dots, and somehow he calculates an error bar in that. Like, I guess he runs the simulation many times. He gets this equilibrium melting point for different gap distances. So this is the gap of his AFM. And then he says, yeah, it matches with the Monte Carlo, which somehow it matches with the Gibbs-Thompson. So somehow he also gets an error bar in the Gibbs-Thompson, because if he didn't, no, it would still work, I guess. But anyway, so it isn't that impressive of a result. Like if you say he cut off at this gap size, you'd say like, oh, it doesn't change. Then he happened to go along a little bit further and he gets 3 points that deviate up with big error bars. So you could just say that's constant if you wanted to. Or you could say it's a trend going up, but it's not the Gibbs-Thompson trend. So that makes you wonder, why does it have that slope, which he doesn't address? So there's kind of problems with this, but it's not in Nature or anything. So it's in Journal of Chemical Physics, which is still a pretty good journal. Still, it's not an impressive result, I would say, given the, maybe it's kind of a goofy question and a goofy paper anyway, because of the last thing, that the surface crystallization could drive the whole thing that he's looking at. So anyway, that's about it for these. Any questions on this one? This one, again, it isn't really necessarily that much about the paper. It's just some questions about surfaces, the equations we did in surfaces, That's about it. I mean, I don't know, it's been a pretty good semester. I've been tied up with that other class a lot, so it's been, this class took the brunt of it, I think, but anyway, hopefully it's okay. Um, So the final is kind of similar to what the qualifier would be, like two papers, some questions about it. But it's really geared a lot towards, well, it's got the same, yeah, this is pretty similar. In fact, one of these questions I asked on a qualifier, so I think this second one. The gel one's a little bit just so you can look and see like thermal in some different system. It's not, that one's not necessarily a great qualifier one, but it's there. So anyway, hopefully that's okay. Any no questions or anything on this? You can email me if you want, and then I guess we're looking at like Friday next week. Like I think that's the last day because I have to grade on. I think grades are due like Wednesday the following week, so hopefully it'll be all right. Anyway, thanks. That's good.